too hard, you wouldn't be able to push the needle out. You'd have like a little spring mechanism or some little.
The upper seisma geophone. This is the lower one. They're exactly half a meter apart. This one detects the arrival time and is the trigger for this one. And we can tell the delta time from using both measurements. The waves will be exact mirror copies of each other. And he takes the second wave and shifts it a delta t over till it exactly matches the first wave. And that's our delta t. guess we'll just go like one slide at a time, and we'll make comments here first. And if you have any questions, just go up to the microphone and make your comment. Okay, that's our site layout. Okay, let's go on down to the first slide. Start. I guess I'll start on this one since I did this test. This was a hole that you can see where we had sand down to about 5 meters. There's some gravel there. It's got pretty stiff here. I think it was more gravel in that area. And then we get into the clays. You can see how the P1 and P0 are pretty close to each other, which will give you a low ID, which will tell you it's a clay. These thrust measurements were made with a load cell. The higher thrusts were in the upper sands and gravels, and then it dropped down as you got out of that formation and then got into the clays below it. These thrust values, I think, we're sensing this lower area, with our stress bulb, is why they go down. You also see, though, the P1 values are going down as well. A little bit of a spike here where it is probably a little bit over consolidated. They're a little stiffer layer in the clay. These clays are believed to be Miocene aged and are fairly sensitive clays. If you did an SPT, you would have very low values due to remolding of the SPT spoon in the formation. They're not quite as bad as what most people would believe if they just had SPT results. I'm going to pass the mic around to my other.
Say a little bit about the geology in the area.
Oh no, I already said what I knew.
You live here. You're supposed to know the geology.
Well, it's some sands, more recent sands and gravels up top, and then you have these Miocene aged clays that are quite sensitive. Yeah.
So the area here where we see an ID of silt, is there a silt-sized particle in there?
I don't know the answer to that one.
Okay, earlier somebody made a question about ID, and Silvano answered it, but I'm not sure that he answered it entirely in that person's mind, so I'll add a little bit to it. The ID is a function of the permeability of the soil, and you can have permeability in a silt-sized particle as very similar to what a clayey sand would be, and I suspect that the crossover that we see there in the ID from sand to clay is actually a mixed material rather than a silt-sized particle. Would kind of make sense for the area. And geology, I was told earlier, is alluvial in the area, but we're talking about outwash from the Appalachians and maybe some coastal plain soils. But this is not a marine clay, right? I mean, is it a marine deposit? Yeah, there's the expert. He actually had to work here yeah, okay. So it is marine. Okay. On this profile, that's the only one comment that I want to make in comparison to what Diego did. In Diego's, and we'll look at this later, but I want to show the absence of a crust here. In the clay, you go pretty much from the sand right back into the clay, and you don't see much of a crust. And Diego's actually shows a crust. So.
I would like to add something to what Paul said about ID, because there is a niche of soil of a given permeability that in which when you go from P0 to P1, which can take A to B, which can take 15 seconds, you have a consolidation, and then your P1 will be lower than it would be if you had no consolidation. So you get a very, very small ID, and this is a silt. So in this case, the interpretation is not good. We found this for the first time with Susan Lacasse in Davin's Gate. I don't remember the site, because all ID were even less than 0. And the reason was that we incurred in this niche, there is this word, of soils in which the permeability is such that when you go from P0 to P1, you have consolidation. P1 may be very, very slightly above P0. Could be in theory even less because you have consolidation. So, but you recognize this by the what Paul, I think, said when he said the crossover is not due possibly to a very clay, but silt which is draining during the test. I think we have similar problems with most in situ tests when you are in a special niche of soil. Anyway, be aware of that. That very small ID could be not very highly plastic clay, but simply a silt which is draining during the test. But in fact, in the program we have a filter that says when ID is extremely low, don't interpret. Or anyway, be aware that does not reflect the material index, but is the fault is of the permeability, which is misleading the interpretation.
Well, one of the things that with ID, we look at the way the soil behaves. So since the permeabilities are different and there may be some cementation and aging, they behave differently. So you're interpreting really the behavior, right? So one soil could maybe behave as another soil if you sampled it. Is that?
I would make one more comment before you go. Go back just a second. You notice here that as the P0 and P1 go up, also the thrust tends to go up. The thrust here really, because we're in a clay material, you're developing friction along the rods. And so the thrust in that material probably is not representative of end-bearing on the blade, which you might interpret for friction angle in the sand, for instance. And that's fairly common to see that general rise with friction on the rods as you penetrate a clay material. Okay.
About 10 years ago, maybe longer than that even, I did some flat dilatometers right up the street for the Smithsonian warehouses. And we did pre-bore the upper 5 meters, 6 meters through that very dense terrace deposits, sand and gravel, even cobbles occasionally. And we got into 2 of those lower Miocene formations, and it's a very, very fine, sandy, plastic clay. It's kind of an unusual material. You'll notice on some of the plots, the KDs are less than 2. Of course, there are some alternative interpretations of OCR and KD that it's not heresy or blasphemy or anything like that from the 1980 versions that allow one to tune that OCR KD relationship up or down based on some other parameters of the particular clay that you're in. But with KDs less than 2, either we could have a slip surface or liquefaction. In fact, it's amazing we're still alive today because we were all standing on that same site. But we did take undisturbed samples and we did test them, and they do have OCRs small, like 1.2, 1.5. I believe we published that in some transportation research record.
We'll go to the next slide. I think it has.
Yeah, you can see there about 4, from about 4.5 to 7 meters at this sounding. But if you look at some of the other soundings that have been shown for this site, some of the KDs are less than 2, yeah. But yeah, it's an unusual material. It's a shame we weren't able to go 20 meters. You get into some very, very interesting material. It's a Cretaceous age. It's actually diluvium from the Great Flood. Remember Noah's Ark and all that kind of stuff, and the Patapsco Formation. That's really interesting. Really hard clay. But the dilatometer picks that up quite nicely. So next time you go out there, Roger, you might want to go deeper.
I think what Paul is saying, if you look at the red graph over here, the KD value, which is shown over here, it's showing a value of about 1 or so from 5 to 7 meters in the very top of that clay. Apologize for the scale, I just didn't show enough decimal places. This is 1, that's 0.5, that's 1.5 and 2.5. But what's kind of interesting with this graph too is it goes back to what Dr. Marchetti was talking about yesterday, in that KD is really an amplification of K naught, and you can see how almost perfectly parallel those two graphs are. The scales are different. The KD value is 4 times as great as the K naught value on this graph. Let's see what else. One of the interesting things with the DMT is that it is a predictor of K naught, and you can see how horizontal stresses versus vertical stresses are plotted, and you can see, you know, where this area here would be a lot softer, where the horizontal stresses are much less than the vertical stresses. But here, where we saw that little rise in the values, you see that the horizontal stresses have exceeded the vertical stress. And we also note that on the undrained shear strength, where it's got a little bulge there. And these plots are based on the ID value, where the ID was less than 0.6. I computed the undrained shear strength because the test occurs rapidly enough that those clays are tested in the undrained condition. The test only takes about a minute to do each one, versus up here I show the drain strength parameters, and I chose that. If you look at recall the previous graph where the ID exceeded 1.2, my assumption is that it's a drain test, because those sands are permeable enough. One thing that was kind of interesting is that this is based on the Schmertmann's method for calculating phi, and it calculates really the plane strain phi angle, and he recommends a correction to get the triaxial value of where it exceeds 32 degrees, of using 2/3 of the excess above 32 degrees plus 32. So to get triaxial values for greater than 32 degrees, that value is equal to 32 degrees plus 2/3 times your value minus 32 degrees. So if you have a plane strain value, for example, 41 degrees, that will give you a triaxial value of 38 degrees.
Well, the only thing I would add to that is that there is apparently some sort of small crust in there, and it actually goes, the SU profile almost goes right through it, straight up down, and you've got a little tip in it here. I didn't see that earlier in yours. It's also in Diego's, just above the weakest spot at about 10 meters, which is also weaker than what you've gotten in here. As Dr. Marchetti said, I think somewhat heterogeneous.
I can see some differences in the way is interpreted the results in the two parts of the ocean. Because, for instance, we don't measure the vertical push to get the friction angle. We measure it, we have a rough idea from the pressure of the oil, which is good to just for safety reasons, but we don't pretend to have a measurement of the QD, or the tip resistance. This is very difficult to do, and I also think would not add much to the interpretation. Measuring the penetration resistance. Of course, you can measure very accurately at the top, perhaps, but in our practice, we see this as a complication that may not be worthwhile for the interpretation, because very often the friction along the rods makes impossible to obtain the tip resistance from what you measure on the top, of course. And to measure locally is very difficult. Or you could have a load cell just above the blade, but then you still have the friction on the blade. So the real solution should be to measure the tip resistance at the last part of the blade, which is very difficult to do for sensitivity reason. Maybe one could come up with a bright idea, but it's a different thing to do. For instance, for phi reasons, we prefer to use another approach that is the one that is being used here, because what I see used here is use this QD, this resistance, the penetration resistance, and to combine with other parameters to obtain phi. We are happy enough to obtain phi from KD using something that was initially proposed by Robertson, and we know that in this way, interpreting phi just from KD without any measurement of thrust, we always say is not the best thing DMT can do, but we think our interpretation is 2 or 3 degrees too conservative, but the complication of measuring is too much a compromise, I think, to measure at the top, because you never know what this will be at the bottom. So we're happy enough with fast interpretation with KD, which cuts out much complication, and so this is the way we interpret the phi. Because be aware that what you are seeing on the on this screen are two different interpretations. This is the interpretation which is made here, which is slightly different from the interpretation in the way I just described, which is the diagrams by Diego, which are later on this screen. So this was especially to point out that we don't measure the this of course has advantages, disadvantages. I don't know how much you lose, but in our way we almost never measure systematically the push force, and we think that we don't lose too much. But this is a matter of opinions, so everybody can have his opinion.
What we here in the United States is the method that's used in Europe is a few degrees too low, and our method that Dr. Spurtman developed are a few degrees too high. So maybe somewhere in between is right, but maybe the average is better. But anyway, the program that is provided to reduce the data does provide the option to look at these various things. But one comment as far as the friction on the blade and the friction on the rod, the program that we have accounts for that, or attempts to account for it. And I think some of the measurements that Paul Bullock, his research showed that the load getting to the dilatometer blade was pretty closely approximated in the program when you compare it to a measurement at the top. Is that right, Paul? But anyway, one of the fun things to me at a conference like this is to realize that we really don't know everything. We're still learning, and there are things that we can improve, and that's some of the things that the people here, the researchers here, we have some practitioners here, so it's really great for everybody to get together and compare notes, and that some of these things can be improved, and maybe we can do a better job with phi.
Yeah, I would just make a quick comment on the friction angle calculation based on bearing capacity is really what it is. with the dilatometer, the bearing capacity area is almost 14 square centimeters, which is roughly 40% greater than the cone. So we have a fairly good amount of end bearing there, and the actual friction on the blade is 1% in the sand or so. So very small number really compared to the end bearing. And so Dr. Schmertman proposed a fairly rigorous analysis to back out the friction angle out of that bearing capacity measurement. In sands, the friction along the rods is very negligible, as is the friction on the blade, so that the end bearing that you measure at the surface is really pretty close to what's going on at the blade. And we do have some data to back that up, not only within GPE, the research that I did, but also before that. So the problem that you were getting into, and I was alluding to this earlier, I guess, in a more offhand way, is that if you test in a clay and then go back into a sand, then you probably have too much parasitic rod friction. And you could make an estimate to take it out, but you would need to be aware of that. So if you're going in and out of different materials, you would need to be aware of that and make a correction. We've had pretty good luck. Dr. Schmertman's had a number of publications on it. So Dr. Marchetti has a good point. It does slow us down a little bit to take that extra measurement. No data is too much in my book, but could never have enough data, right?
Along the same lines with the rod friction issue, I've noticed in a lot of the soundings I've done, we've measured head load. There seems to be it starts out fairly high and begins to drop, regardless of what soil you're in. You're talking about a 20 centimeter increment. Is that enough push distance to relieve a lot of that rod friction? I've done some with a little bit tighter increment, and I've been noticing that maybe the thrust is still not down to maybe the full release of the rod friction. You guys have any comment on what is the best push increment to get to try to release as much of that rod friction as possible?
I think that delay and thrust where it drops off as you push is more attributed to pushing through a clay when you're mobilizing and remolding the clay. If you're in a sand, I don't notice that type of drop off. The sand thrust values seem to be they're a little bit more scattered. They're not as constant, and I think that's just due to the cementation and particle size as you push in the sand. What we do is always take the thrust reading right at the test depth and just use that value. I don't average whatever it is over 20 centimeters. We just push. But I think really within a few centimeters we notice that the thrust will stabilize in the clay, but we don't really use the thrust measurements in the clay for any calculations. I use the thrust measurements to give me a guide, though. If I'm in some higher thrust material, I'm probably in a sand, and I may have higher A and B values. If the thrust suddenly drops to a real low value, then I, as an operator, feel that I may be going into a softer clay, and I instruct my operator, Barbara, if you have some low thrust values, say less than 500 kilograms of force, we often run tests at 10 centimeter intervals just to get a better handle on that. I'd rather get twice as much data in a real soft layer, because then that can be the most critical thing to the whole project. A 2-foot real soft layer, if I have twice as many tests, is a lot more valuable for the settlement analysis. This one shows the stiffness, constrained deformation modulus versus depth. Again, we see that bulge where we had that stiffer, almost like a crust in the middle of the clay formation, at least where we tested. It's pre-consolidation, pretty much almost like normally consolidated right here, and then you have an over-consolidated zone, and then you dip back down to just lightly over consolidated, then it goes back to more highly over consolidated.
Well, I guess I have the same comments as before, so. Anybody want to add some of that? Let's move on to some of the others.
Okay.
I actually think it's another layer. It's very complex geology around here, and there's probably 2, if not 3 water tables.
Okay, I guess we should move to, should we look at the seismic DMT that went deeper, or should we look at the, let's look at the, go down quite a few slides so we can keep going. Let's go through we want to skip these holes and go to the seismic DMT. Yeah, let's stop at this one. I think we see the same, you have your higher KD values here. Again, you have your sands. I don't think we saw this in-between material in that other hole, even though it was pretty close. I'm not sure why. And then we get a drop off and get into some clays. We see this bulge again on this hole, like we did on the hole I did. So it to me, it tells us that shows the repeatability in picking out some imperfection right there, an irregularity with the DMT, and how well it will repeat itself.
Well, if you were putting a building out here, then certainly that extra little strength there is going to be quite a helpful addition. Might have some concern about the stiffness of the material from about 4 to 8 meters in terms of settlement, and maybe even in terms of shear strength. What's the building that's there built on? Do you know? Shallow foundation. Any minute now it could come down. So fairly weak, kind of scary. Do you have any comments at all?
Maybe the only comment is about 10 meters, the ID. Possibly 10 meters, this ID so low could be in the niche that I mentioned before. I don't think, or it may be possible. It is possible that this is not very clay, but is just a silt, permeable, relatively permeable, intermediate permeability silt. Another thing I want to say is, since ID is a single parameter, of course it's not a sieve analysis. So if you have a mixture of sand and clay, I'm saying things which are obvious, but just in case. If you have a mixture of sand and clays, probably they will be interpreted as silt. So the interpretation will be wrong, but in practice will be better because the mechanical behavior is the one of the silt. So from the sieve analysis viewpoint could be wrong, but from the mechanical viewpoint could be a silt because it behaves like a silt. So we must understand the limitation which are in the ID, which is not the main purpose of the instrument, but anyway is helpful. And the second comment may be about this bulging at between 8 and 10 meters. Again, we see this bulge quite evident in the second, third, and fourth diagram, but is very not very much evident in the last diagram. Maybe there is about 8 meters, 8 point something meters, some bulge, but it's a very reduced bulge. And it's interesting the fact that the initial 4 diagrams are completely independent from the the fifth diagram. So in a sense, they can check each other. I just wanted, with this statement, to point out that the additional fifth diagram is completely independent from the initial. It's nice, of course, to have all together, but is a different nature of the measurement. So in fact, we can see at 2 meters there is some parallelism. So it is confirmed at 2 meters that even by the fifth diagram that we have lower values. So these are my comments.
I guess my comment's more of a question, Dr. Marchetti. The shear wave velocity does correspond to KD at this particular site. Do you have any comment on that? Compared to the site that you had that the shear wave velocity wasn't sensitive to changes in KD? Maybe this is the case that both would be a good parameter for prediction, and the other site, maybe KD would be better. Is that a good?
So in this case, the bulge is in a zone in which we have no sand. So since we were talking about liquefaction, I immediately looked there, but it's no sand. So though the bulge is more evident, but we cannot say it's more sensitive to liquefaction, because liquefaction is not an issue in this case, because it's not sand. Maybe the observation was simply that the bulging is more evident in the other diagrams rather than in the last one. Oh yes, you are right. In the surface, yes, KD is much more brisk. Can you say brisk? Active, variable, and the shear wave velocity is a little more lazy. Let's say, moves in a lazier way. It's less evident. Of course, one could plot G0 in which you have the square, so probably the would be amplified, the variability, even in the fifth diagram. But we always found that even if you plot G0, G0 is lazier, more lazy than KD or M.
I guess we'll go through the other stuff real quickly, but we're kind of getting behind time. I didn't really just go down from there, yeah. You just want to go through, if anybody has any comments, we'll just go through these quickly. Okay, keep going. I think this one, I think the last reading looks an oddball, but.
On the earlier comment about damage to membranes, I guess I want to bring this up. In our little demonstration at the site, we were fortunate from the experience standpoint to have 2 membranes that were damaged. So, it lets you know that you can damage them. In this particular case, I think it's because we probably had a little gravel on one side of the membrane and soil on the other. Now, I would throw out the last data point, and that's one of the things that the operator really should do. On his data sheet, he should say, we overextended the membrane, and we discovered that basically when we moved to or tried to move to the next level. So, and when we pulled it out, well, we confirmed it. But membrane damage can be due to a number of things, and we've already mentioned the fact that you can have gravel. And if you're testing in sharp, angular gravel, you can cut the membrane. And as Dr. Marchetti said, that's the most common way that water gets inside the blade. The other thing that can create problems are you can be in a noisy environment. People can walk up and distract the operator, and he overextends the membrane and really doesn't want to admit it later on. I'm not saying that this was a particular case, but I think one of the real learning lessons in this demonstration was in the track-mounted rig that Roger gave me the pleasure of working with. It was very noisy. And I wanted to point out that the control unit has redundancy. We even have a place you can plug an earphone in if you want to try to get rid of that noise. We have a light, which we used yesterday. We have a galvanometer, and then we had a buzzer. So you have 3 different ways that basically you can keep up with the pressure the time to read the pressures. But anyway, operator error is one cause of membrane damage. And getting back to Dr. Marchetti's comment about having a even stronger membrane, I think that'd be great if you always have a soil that's increasing in strength with depth. But if you go through something very strong and then get into very weak soils, then you can have a big change in your delta A and delta B readings that you may have trouble separating out when you get down into something softer. So there are some cases that certainly would be good. If you're going to try to test gravel, well then maybe we need it. But
when I said stronger, I don't mean stiffer. I mean same thickness, but the steel can be hardened in some way, or the surface can become stronger. So of course because if you have a thicker membrane, then you have delta A and delta B, which is too big, and then in soft clay would not be good. So you have to keep the membrane, but the material same modulus but higher strength.
I'm just gonna go through the slides. I don't know if there's. I don't have any further comments. Does anybody else have any comments? I think that the field exercise was just a good opportunity for people that didn't know how to do the test to get at least a little warm and fuzzy feeling about doing the test and how to do it. And doing that helps you feel more comfortable using the data.
Well, I'll only add one thing for the benefit of being able to hear in the loud, noisy environment yesterday. In the ASTM specification, something that Dr. Marchetti has been very adamant about for a number of years, and that is the proper time for the readings. You should take about 15 to 30 seconds to get the first reading, that period of time again to do the second reading, which means the test should be completed within about 30 seconds to a minute if you're just doing A and B. If you do the C reading, then another 15 to 30 seconds. And that's an important part of doing the test. Number one, it makes the test move along quicker. You get a lot more soundings in the same one day. And number two, if you're testing in a mixed material where the permeability may change the readings during the period of time during the test, that you get relatively consistent readings from operator to operator. So very important to pay attention to how fast. And that's new users always tend to be wrong in the period of time that it takes to run the test. It's just that you're reading the gauge too closely and you take too long, or you're pressurizing too fast and you go too quickly. It's worse probably in very, very soft soils, which we were getting into with those clays, where the readings are low and you have to force yourself to slow down to get within that 15 to 30 second range for each reading. So it is an important detail.
I didn't see how the other people were conducting their test, but you know, I really didn't enforce the time limit that Dr. Marchetti would enforce because of the reason that Paul said. You know, that's something that after you get just a little experience, then you can get that speed, which also increases production. But it's also important in the beginning to have a more accurate reading than to be way off. So we really weren't enforcing the times that Dr. Marchetti would really like to have. So for you, benefit of you people, your production would be greater than you saw in the field with what we were doing with new operators.
Yes, I strongly agree that with both of you said, because you have two advantages. You make the test in the proper way and the production increases a lot. Actually, what we do is we go not at a variable speed. Once you have taken 10 readings, you become quicker because you know that at the beginning you can go fast until say half of where you expect the reading. Then you can slow down and just freeze the almost taking the reading when the needle is stopped, and then you immediately increase the velocity, and then you break in the proximity of the next reading, and this is increases a lot of productivity. I've seen many people saying, "Oh, I had to look so carefully," so they go from 0 to 5 bar at the same speed. This takes a lot of time and is useless. You go very fast to 4 bar, to 3 bar, and then, of course, it could be that in this way, when you have a change in layer, you miss the reading. But in this case, you say the operator, go 5 centimeter ahead, repeat the reading, and then do the rest of the 20 centimeters, so you can repeat the reading. So I think this is really a detail, but from the practical viewpoint, I think it's important that you initially go fast, then you stop in proximity of A, then you increase the speed, and then you brake just before the expected second reading.
Okay, I think we should take a short break, and time is it, Paul? 10:30. Okay, maybe take a 15-minute break.